we're going to talk about different parts of polynomials and what information they can tell us. And we need to get a little bit of preliminary information before we can get into some of the more logistical things of polynomials. And the nice part is, if you're good in English and you know your prefixes, you will probably be able to define some of these things with ease. For example, the first problem, a monomial. So the prefix of monomial is mono. What does mono mean? Tiffany? Single or one. This is a one-term expression. That is a number, a variable, or the product of numbers and variables. So product means that they're multiplied together. So, for instance, we can say 4. 4 is a monomial. X is a monomial. There's a number, there's a variable. The product of a number and variable, 4 times x, we can multiply those two together. Keep in mind that it could also be something like x divided by 4. That's still a monomial. And if we want to get fancy, we could say x to the 4th. It's still a monomial. Our next word is polynomial. Well, what does poly mean? Tiffany? Multiple or many terms. And this one is, a polynomial is either a monomial, or it can be a lot of monomials added together. The sum of many monomials. But I got ahead of myself, but Tiffany just told us a moment ago that polynomial comes from the word many terms. But the confusing part about polynomial is that it can be a monomial. So it could just be 4. That's still classified as a polynomial. Or it could be x plus 4x plus x over 4 plus x to the 4th. Or it can be the sum of many of them. I've talked about it before, but here's the formal definition. The standard form. The standard form of a polynomial function arranges the terms in descending order. What I mean by descending is we start with the highest exponent and then we get smaller and smaller and smaller. So descending. Descending numerical order. It's based on the exponents, based on the powers, not the coefficients, not the numbers in front. We go from highest exponent to lowest exponent. And then we talked about this yesterday. The degree of the polynomial is the highest exponent that any of the monomial terms have. So if we write our polynomial in standard form, then we should be able to look at the first term and identify what our degree of our polynomial is. So what we're going to do is we're going to classify our polynomial by degree or by its number of terms. And we have special names. Polynomials degree 0 through 5 have specific names as given in the table below. So the first degree that we're going to deal with is the 0 degree. And here's an example of a 0 degree. It's 5. What do we call something like the number 5? Tiffany? It's a monomial, which we can put that's the name using the number of terms. because there's only one term there. But if it's just 5, the name of a 0 degree is called a constant. So when we get to our degree 1, here an example of degree 1 is x plus 4. If we graphed y equals x plus 4, what does it look like? Well, it looks like a line, so we call degree 1 a linear function. X plus 4 here, how many terms are in x plus 4? 2 terms. And we have a special name. We haven't looked at the words there, but again, if you know your prefixes, what prefix represents 2? Like bicycle has 2 wheels, binomial has 2 terms. Next one, degree 2. Done a lot of work with degree 2. 4x squared is an example. What do we call something of degree 2? Starts with Q. Quadratic. Again, our polynomial example is 4x squared. How many terms in 4x squared? And hopefully you're thinking 1. And if we can identify the fact that there's only 1 term, then we know that that is a monomial. We can see that on our 0 degree. And then we might get into some that you're not familiar with. But I was hoping for those first 3 that we were. But 3rd degree. A 3rd degree is called a cubic polynomial. In our polynomial example, we have 4x cubed minus 2x squared plus x. How many terms do we have in there? 3. And again, we haven't talked about it, but if we know our prefixes, what's the prefix that represents 3? Tri. So it's trinomial. Trinomial. Tricycle has 3 wheels. Trinomial has 3 terms. Fourth one. Again, another one that I'm not sure you're familiar with. And degree 4 is a quartic. It's Q-U-A-R-T-I-C. And in terms of our polynomial example, we have 2x to the 4th plus 5x squared. How many terms in this polynomial? 2. And we see above in red that our 2 terms, we call that a binomial. And finally here, our 5th degree is called a quintic. Q-U-I-N-T-I-C. When we look at our example, negative x to the 5th plus 3x cubed minus 2x plus 9, how many terms do we have? 4. And then the name of the term, well, after 3 we don't really have any special name, so we can call it a polynomial. or a polynomial of 4 terms. As we look at the bottom of our paper now, it says write each polynomial in standard form, and then classify the polynomial by degree. So when we classify our polynomial by degree, what we're going to be doing is we're going to be over here, the constant, the linear, the quadratic, cubic, quartic, quintic. That's what we're doing when we're naming it by degree. We have to write it in standard form. Standard form means highest degree term first. So when we look at this one, 9x squared is our highest degree, plus 3x plus 5. Highest degree, then next highest degree, and then eventually we end with our constant. What's the degree of this polynomial? And if you can't shout it out, at least at your desk, put up the fingers. You don't even have to show me. Show yourself. The degree is 2. And now the classification of a second degree polynomial, when we look above at our table, and a second degree polynomial is the one that we've had the most experience with, lately at least, the quadratic. So we come over here to our second example. What's the first thing that you notice on the second example, if anything, Jordan?
There's more x squared.
There's a couple of x squareds here. But what's our highest degree term? That's what we were looking for. We have to watch out for that. Highest degree term? So it's going to be x to the 4th. But then our next highest term is going to be the x squared. And when we combine like terms, we're going to take negative 6x squared plus 10x squared, and we get plus 4x squared. So we've taken care of those 3 that are marked, which leaves us with the plus 4x and minus 12. We just wrote that in standard form. What's the degree of this polynomial? It's the highest degree term, so it's actually 4. And then when we look up above there, at our classification, a 4th degree polynomial is called a quartic. So again, some of you are working ahead, and I certainly have no issue with that. But when we write it in standard form, we want the highest degree first. 3x cubed. And then the next highest. And then eventually we get to our constant. If we can write it in standard form, our degree comes from our first term, which is the 3. And it's the exponent of 3, not the coefficient of 3. When we look above to see what a 3rd degree polynomial is called, we see that it's called a cubic polynomial. And finally, when we look at problem number 4, well, it's going to be 2x to the 5th, highest degree exponent first, minus 4x squared. Our degree is the highest exponent, which is 5. And what do we call a 5th degree polynomial? And remember, you can look at your chart. It's called a quintic. Jordan? Got it. Okay. So we flip our page here. What we've done now is we've got the names of the polynomials. But we're going to look at the end behavior, and more about the degree. And the degree of a polynomial is one of the most important things that we can know because it gives us some information. For instance, it tells us about shape. We're most familiar with the shape of a quadratic because that's what we've really spent a lot of time on recently in class. But it can also tell us the possible number of turning points. And we explored that some yesterday. And then it can also tell us about the roots, which sometimes are called zeros. I like the word roots, but some other teachers like the word zeros. The solutions, the x-intercepts of the function. And keep in mind in there in that parentheses that roots can be real or they can be imaginary. But we're not really going to get into the imaginary today. But that's the degree. As we jump down here, we can talk about the end behavior. We, again, started some of the end behavior yesterday. We said, what's the end behavior coming from the left and what's the end behavior coming from the right? So we're going to make it a little bit more formal within this chart. And our first function here, y equals x squared, like I said, the most familiar to us of our functions, which is the quadratic function. Our degree is 2, and I want to go back up there and look at our directions. I started good, but I left the directions out. There are 4 types of end behavior that our graph can take, and they are shown below in our pictures. We want to identify the degree of the polynomial and whether the leading coefficient is positive or negative. And that's going to give us some help to determine our end behavior, which is at the very bottom of our chart. So our degree on this first one is 2. It's y equals x squared, which means that our coefficient is positive. And at the very bottom of our chart now, what it says is it says x arrow negative infinity. Well, x arrow negative infinity means that the x values are going to the left. So we're going towards the left. What's happening to our y value when we go to the left on the graph? Well, what's happening to our y value is it's continually going up and up and up and up. So what we're going to say is that y is going to go to infinity. Well, if x approaches, which is technically what that arrow means, x approaches negative infinity, that means going to the left. X approaches positive infinity means that we're going to go to the right. And when we look towards the right on our graph, what our graph is doing is going up and up and up and up, which means that y is also going to approach infinity. And we got introduced to that a little bit yesterday. If we look at the second box here in our table, what's the degree of that function? And again, if you're not saying it out loud, just do something so that in your head you're saying that. It's 4. Is our a positive or negative in this case? It's negative. It's negative x to the 4. So when we look at this one, as we go to the left, x approaches negative infinity. What's happening to our y value? So negative infinity on the graph going left. What's happening is we're going down, 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 down. So this is going to approach, our y is going to approach negative infinity. And as we go towards the right on the graph, x approaches positive infinity. As we go toward the right, y also ends up going down, 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 down. So it also is going to approach negative infinity. When we look at the third box, y equals x cubed minus 4x, what's our degree? Again, at least do something like that to tell yourself that it's 3. Is our coefficient positive or negative? It's positive. x cubed, there is no other indication. It's just x cubed, so it's positive. And once again, x approaches negative infinity. That means we're going to the left. As we go to the left, what's happening is that our graph is going downward. So this is going to be negative infinity. As x approaches positive infinity, our graph is going upward. So we're going to go to positive infinity. And I think I said that right. As we go to the left, our y values are going downward, negative infinity. As we go to the right, our y values are going upward, which is positive infinity. And then, when we look at this last one here, we have a degree of 3 again, but we see it's negative x cubed, so we have our negative value there. And when we read the graph, as we're going to the left, x approaches negative infinity, our graph is going in an upward direction. But as we go towards positive infinity, which is going towards the right, then we're going to get negative infinity. And well, let's summarize here our end behavior. But again, there's 4 types of end behavior. And we've got them in our chart there. So it looks like if our degree is even, then both arrows at the end of our graph either go towards infinity or they go towards negative infinity in the y direction. If the leading coefficient is positive, so if we look back at our chart, if the leading coefficient is positive, it looks like both of them are going to go towards positive infinity. But if the leading coefficient is negative, then both of them are going to go towards negative infinity. If our degree is odd, so those first 2 degrees even, x squared, x to the 4th, down here our last 2 boxes had x cubes in them. If we have odd, one arrow goes towards negative infinity and one goes towards positive infinity in the y direction. And if the leading coefficient is positive, then the graph tends to have a positive trend. And what I mean by positive trend is that our graph starts low and gets high. So consequently, if the leading coefficient is negative, then our graph would have a negative trend. So it would start high and get low. So as we look back at the picture, it's hard to explain on the video, but when our coefficient's positive, we started low and we ended high. When our leading coefficient is negative, we started high and we end low. Just maybe some way to help remember. So turning points. Turning points tell us how many times a graph changes direction. So for each of the following degrees, we're going to sketch a graph describing the possible number of times that it can change direction. So when we start here, it doesn't matter what line you draw. I was trying to draw one from corner to corner. How many times do we change direction? 0 times. We started here at the left corner, we went all the way to the top, we never changed direction. When we look at our quadratic, if I draw a rough sketch of the parent function of a quadratic, how many times do we change direction in a quadratic? We only changed once. Right here. We went down, we got to the lowest point, and then we went up. How many times the graph changes direction? So when we look over here at cubic, we actually just drew a couple of cubic functions. One of them looked like this. The other one looked something like that. But either way, how many times do we change direction in a cubic function? Twice. 1, 2. 1, 2. For a quartic, you may have to look back at your notes from yesterday to see a couple pictures of a quartic. One of them that we drew yesterday in our notes looks something like that. But it can also look something like this. Again, regardless of the picture, what we're trying to figure out is how many times do we change directions, and that's referring back to our turning points. Oh, in either case, we change directions how many times? 3 times. Here, here, here. And let me write it so you can see it on the video. Here, here, here. Or here, here, here. That's where we change directions. 3 times. So when we summarize this, again, back here, linear, we had 0 changes, 0 turning points. Quadratic, we had 1. A cubic, we had 2. A quartic, we had 3. In general, there's a pattern. What do you think it is? Matthew? Not the exponent, because in a linear, our exponent would be 1. In a quadratic, our exponent's 2. In a cubic, our exponent's 3. And in a quartic, our exponent's 4. He's leading us in the right direction. Oscar? It's 1 less than the degree. So I tend to write this as n minus 1, but I'm going to write down what he said. 1 less and the degree. Which you may have to squeeze in on your paper if you're going to write that down. Not a lot of space there. So we've named our polynomials. We've looked at degree. We've looked at end behavior. We've looked at turning points. The last part that we're going to look at is the number of roots. How many unique x-intercepts does the graph have? Again, that's a root, that's a 0 x-intercept. So for each of the following degrees, we're going to sketch a graph describing the possible number of unique roots. And I'm going to start with the graph that I drew just a moment ago for our line, which roughly that was our picture. How many x-intercepts do we have when we draw our line from corner to corner? Just have 1. The question is, why did I put it here? But if we look over here, I could have drawn the line. Ooh. Hopefully yours is straighter than mine. But I was trying to draw a horizontal line. How many times does our horizontal line cross the x-axis? Does it cross the x-axis? It doesn't cross it at all. It crosses 0. So here on our second graph, we cross the x-axis there, but we don't cross it. Why didn't I draw a vertical line? If I drew a horizontal, why didn't I draw a vertical? Hey? It would only cross once. So there's our linear function. When we look at our degree 2, our quadratic, the one that we are most familiar with, when we draw that here, we could draw a quadratic with 0 x-intercepts. Something like that. We could draw with 1 x-intercept. Or we could draw with 2 x-intercepts. Again, your pictures don't have to be the same as mine. But degree 2, there's 3 ways to draw it. If we look at our cubic functions, let me pause for a second to get people caught up. So if we look at our cubic function, I want to show you one particular picture. Here I have it on there. But what I typed into the calculator was y equals x cubed. This is the parent function of a cubic function, which we haven't really dealt with much. But when we graph y equals x cubed, that is the picture that we get there. So if we draw that one first here, what we see is that we cross the x-axis one time. And then we've got our standard ones, or at least similar pictures that we have seen yesterday and today. Well, we must be able to draw a cubic function with 2 x-intercepts. So we can draw something like this, where we cross the x-axis here and we cross the x-axis there. And we can also draw a picture where we can cross 3 times. We've got an x-intercept here, and an x-intercept there, and an x-intercept there. Again, your pictures don't have to be the same as mine, but these are samples to represent the different x-intercepts, which are also known as roots and solutions and zeros of the function. Quartic. Whoa. Got a lot of options in the quartic. But you probably have seen kind of a pattern. The question is, can we draw a quartic with 0 x-intercepts? And in fact, again, referring back to yesterday, we had a picture on our activity that looks somewhat like that. We never cross the x-intercept. Well, we can probably go right down the line here for 1 x-intercept. Something like that, where we only cross here. Well, 0, 1, 2. We crossed here and we crossed there. We could do 3, and I'm trying to switch it up a little bit. I think. I'm just trying to look and see if I can do it. I don't know if I can. 1, 2, no. Let me try again. 1, there we go, 2, 3. Here, here, here. So there's 3. And I'm just drawing different end behaviors, that's all that I'm drawing. But we've done 0, 1, 2, 3, we must be able to do 4. So 1, 2, 3, 4. And let's see if we can summarize this to finish here, or at least get close to finishing. It appears that the maximum number of unique roots or x-intercepts a polynomial can have is equal to what? So looking at the maximum. A quartic, we had degree 4, we ended up with 4. Degree 3, the maximum was 3. Degree 2, the maximum was 2. Degree 1, the maximum was 1. What's the pattern here? Well, it's equal to its degree. And then finally here, just one last note to leave you with today. While the number of unique or different valued roots or x-intercepts varies for each polynomial, a polynomial will always have as many solutions as its degree. The thing is, the solutions can be real, but the solutions can also be imaginary. And we're going to be exploring that throughout our time of polynomials, which is going to be really for the rest of the school year for the most part.